Welcome everyone to another episode of the Blaspheming Bite. Today we're going to look at another Leetcode problem. Looks like YouTube would rather have me do Leetcode problems than problems from books that people don't care about. So sticking with the topic of trees, we're going to look at this question called given a tree, how do you find the minimum depth of the tree? So the question is given here. It's a Leetcode problem, and it's given a binary tree, find its minimum depth. Okay, so you go through all the different parts of the trees and find one that's the smallest. Now, real world application of this would be where, let's say, you want to find you have answers lying all across the globe, or you have nodes all across the globe. You want to find the shortest. Like you have answers lying all across the leaves, and you want to find one guy that's closest to you, like the minimum number of hops. So that could be some sort of a use case for this. Now the definition of minimum depth is the number of nodes along the shortest path from the root down to the nearest leaf node. Now Leetcode has given us a hint, right? It wants us to find the answer to this. So it's telling us, oh, okay, node, a leaf. What's the leaf? A leaf is a node with no children. Now that's a major hint, okay? They're basically giving away the question there. They're basically telling you, okay, um, this is an easy question, but very few people have solved it. Like the number of people who have solved and gotten accepted is like 37%. Something wrong there, right? That's why I thought, okay, let's do this question. Like, what's wrong? Why are people getting it wrong? And I cannot understand why people are getting it wrong. The solution is pretty straightforward. You just have to do a basic DFS. Now, coming to DFS, okay, let's look at this example here. In this example, we are given a tree, 3, 9, 20, 15, 7. Now, if you go down this path, what do you get? You get the height as 3, right? What if you go down this path? You get a height of 3. If you go down this path, what do you get? You get a height of 2. So that's basically what we want to find. I think in this definition of the height, they are including the root node. Our definition generally excludes the root node. So that's basically it. And the answer that you want to find is when you go from 3 to 9, that's basically the minimum depth. Great. Let's look at some examples of how we're going to do this, of how we're going to solve this problem, right? The key thing to remember is the leaf node. So first thing you want to do is, for example, in this example, what are the leaf nodes here? You have this guy, you have this guy, and then you have this guy, right? What do you mean by a leaf node? Leaf node is, again, he's defined it for you. A leaf node is a node with no children, right? We talked about children and career in our intro to trees, and please go and watch that video if you need a basics in trees. So we have 3 candidates, right? We have 3 candidates for leaves here, and we want to see, okay, what's the minimum distance? Now let's just look at this and see what the values are. So if you look at this guy, the value is going to be 3. If you look at this guy, the value is going to be 4. If you look at this guy, the value is going to be 5. Now, what does this give us a clue? It gives us a clue that you actually have to go through every single node in the system. Like, so basically your time complexity would be overwhelmed. You really want to go through every single guy, right? Because in this example, you started from the left, okay? You keep going depth first into the left subtree, right? And then you got a value 5. But then you have to look at the next guy, right? You have to go here and see, oh, okay, what is this subtree? So now you would think that, okay, 4 is the minimum distance, but no, you keep going down, then you reach here and you say 3. Okay, now that is the actual answer. Okay, let's look at another example, and then we can look at how we're going to do the code. Okay, Now let's look at this example, right? In this example, you go like, so what are the leaves here? These are the leaves, right? And then you've got one leaf here. What's the height for this guy? It's going to be 3. Height for this guy is also going to be 3. Height for this guy is going to be 1, 2, 3, 4, 5. Okay, so we obviously want to get either this guy or this guy, right? Now you might think, why don't we break earlier, right? As if there's a possibility that um, you don't have to do this further. You can just break, but you have to go through everyone, like, because we saw in the previous example, you have to go all the way and check every single leaf, because you don't know. Yeah, you might have somebody who is lower than the current value you've got. Now, how do you actually solve this, right? Like drawing this seems to make it easier, but what do you actually need? There are 3 things that you're going to require to be able to solve this problem. One is DFS. So you know what DFS is: depth first search. You keep going down, 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 and then you reach a leaf, and you're like, good. And when you, as you go down the leaf, you have to keep track of the height, right? So every time you go down one level, you have to increase the height by obviously 1, right? And then you keep you check the height when you reach a leaf node. So what's a leaf? A leaf node is a node with no children. When you reach there, you have to check, okay, my current height that I've been keeping track of earlier, and I'm going to have another variable. Okay, there's going to be another variable here which is going to be tracking the current current values of minimum, right? So once you reach a point where you're at a leaf, you're going to check, okay, I've reached this leaf. What is my height right now? And is my height less than the minimum height right now? So what did you do at that point? You would update the minimum height. And that's kind of what we're doing here, right? In our previous examples, so when you were doing DFS, you would set your minimum value to 5, okay? And then you go back and then you go to the next one, and then you realize that, oh no, there's 4 that's lower, so use an update to minimum value. And then you go again, and then you say 3, and then you update the minimum value. So those are 3 things that you'll have to do. DFS, keep going through every single node until you reach a leaf node, and then you check the height, keep track of the height, make sure that you're updating the height at every point. And then once you reach a leaf node, you compare, okay, the minimum value that I have right now, is that like the lowest that I have? Is that the lowest possible? If the height is lower than the minimum value, then just update the minimum value. That's basically it. Moving on to the code, let's look at the code. So the code is not mine. I've taken it from one of the Leetcode submissions. I thought this was the easiest to follow, so let's look at it. So we talked about a minimum value, right? And that minimum value is defined here. Okay, that's where you start off. You start off with that. And this can be int max, because you can assume that any value that you get, assuming that your tree is not as big as the height of your tree is not as big as int max, you'll always find somebody who's less than that. So you initialize it to the maximum value, and then when you find somebody who's lower, okay, yeah, let's go and update them. Okay, that's the whole idea. Now the recursion that we look at is this. If you reach, the base case is if you reach an empty node, then just return, right? Don't do anything. A null node, sorry. If you reach a null node, yeah, just get out of there, like get out. You have no business being there. But if you've reached a leaf node, and that's the condition over here, okay? This leaf node here. Oh, that's ugly. Uggo. So if you reach a leaf node, what do? You have to, so we've reached a leaf node. So we have to next step is to check, right? And how are we going to check? We're going to check the current height if it is less than the minimum value. Okay, if it is, then you go ahead and update the value. Pretty simple, right? Now if none of this works out and you don't update the minimum value, it's fine. You still have to keep DFSing down. Okay, you have to keep going down, and every time you go down you have to update the height. And that's where this part comes in. Okay, so we talked about this earlier. Every time you go down a level, make sure you increase the height, right? And that's how you do it. So 3 things that you have to take care of when you're doing this question. Number 1, understand what a leaf node is. Leaf node is a node with no children, right? It ain't got no children. Second thing is you need to know DFS. DFS is basically where you go through every subtree, right? They keep going down, 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 down until you reach leaf node, and then you come back up. That's basically DFS. The other one is breadth first search, where you go level by level. Second thing, make sure you're keeping track of the height, right? Every time you go one level down, make sure you increment the height by 1. And then at the final point where you've reached a bloody leaf node, what do? You've been keeping track of its height, right? Check if it's lower than the minimum, right? If it is lower than the minimum, then oh yeah, just go ahead and update. That's it.